All right, so one other thing that I want to tell you about today, although we are not going to do a lot of real algebra machinery, just letting you know that this thing exists, is all the trusses that we have been doing. If you look at the problem and the solutions, these trusses have been statically determinate. When you get to your 3 degrees of freedom, so when you write your equilibrium for the 3 degrees of freedom, equilibrium for the 3 degrees of freedom, the number of equilibrium equations that you have up to now was always equal to the number of unknown axial forces in the bar, right? All the problems you have seen and you will see in 201 are problems in which the number of free degrees of freedom of the free joints, so that the number of equilibrium equations that you write for the free joints are equal to the number of the unknowns. So in this case, I have one joint, let's call it J, that is free. The other one are constrained. Equilibrium X, equilibrium Y. I find the axial force in this bar and the axial force in this bar. 2 equations, 2 unknown. So sometimes, though, life is not as simple as that. And some people may want to give you some extra help to hold down this joint. Say that I put 2 more bars like that, so that now this joint has been held up by 1, 2, 3, 4 bars. I do not have any extra equilibrium equation. I still have only 2 equilibrium equations. So in this case, I have 2 equilibrium equations and 4 unknown n. This truss here is statically indeterminate. This is a SI truss. And SI trusses are a little harder to do, right? Little harder to do the SI trusses. So we are not doing SI trusses in 201. That's a good news. I'm going to tell you a few things about the procedure by which you would solve a statically indeterminate truss, because it's an interesting kind of thing and important to kind of let you go forward. So the way you solve statically indeterminate trusses, you can try to go back to your good old force method. Or you can go another way and use a displacement method. All right, so what would you do with the force method? You would say, I know what the trick is. It's just that you have redundant bars, the same way as we had redundant support for the bar between 2 walls. These guys are there, but they're not required. They are redundant. So the way you deal with that in the force method, you take away this redundant support. You say, I don't need them. You substitute them with the axial forces in the bar, N1, N2, and whatever, that now you treat as if they were additional loads on joint J. You solve the structure in terms of these unknown loads. And then, after you solve it and you have this displacement of the joint in terms of these forces here, you say, wait a second, these were not free, they were attached to a wall. Now you remember that there was a wall. And you say, guess what? This displacement of the joint cannot be anything it wants. It must be connected through the forces in the bar. It must be connected to the forces in the bar through the stiffness of the bar. Because if the joint displaces, the length of the bar changes, so the axial force in the bar changes. And so you can end up with a system of equations in which you impose the compatibility at the redundant bars, and you solve it. It gets nasty, okay, especially if you have a lot of extra bars. Say that somebody wants to hold up this joint and want to make sure that it's not going anywhere. So it's attached to the ground by a lot of bars and you know, they're all helping. And they think they're doing good, and you think you're not doing good. That's a lot of unknowns, right? But you can solve it that way. Another way of thinking of this is to do something very clever. So I'm going to put in like the little light bulb here, because it's such a good idea. So the good idea of the displacement method is to realize something really great. What you realize is that the master, actually, let me write it here, right there. The master unknowns are not the forces in the bar. They are not the character that control the game. They are not the queens of the ball. The master unknowns are the displacements of the joints. The free displacement of the joints. So if I have only joint J, my UXJ and my UYJ, these guys are the real queens of the ball. These are the ones that control the solution. Why is that? Well, if I knew what was the displacement of this joint, say that I come to you and I am like the oracle, and I tell you, I see the displacement of the joint. It is 2 centimeters to the right and 3 centimeters down. You say, really? And I say, yes, of course, I'm teaching you. You can trust me. So you say, okay, so the joint move a little bit to the right, a little bit down, so it looks like that. Now the truss would look like that. If I compare the length of the bar before and the length of the bar now, I have the elongations of the truss. I know, if I know the stiffness of the truss, I know the axial forces in the truss, right? So if somebody comes to you and tells you where the joint is gone, he's telling you how long the bars have gotten and what forces there are in those trusses. The N that used to be your unknown before turned out to be just somebody that goes along for the party, right? They're not the master that controls everything. The displacement of the joint is the master. And so, if I think in these terms and I express every single, so these are the real unknowns. So I can write the axial forces are axial forces functions of the u's. So of all the unknown displacement of the joints. So I can express all the axial forces in terms of the unknown displacement and then put this one into the equilibrium equations.
How do you put it in terms of the displacement?
It's actually a lot of machinery, because in order to put it in terms of the displacement, I have to look at the shape of the bar, look at the original shape of the bar, project the displacement along the bar to find the elongation, multiply the elongation by the stiffness, and I find N. So my N is going to be like UX cosine theta times K. Okay? So there is a lot of algebra and machinery and scalar products of vector, but is totally doable. Okay? Just a lot of extra machinery to do. But once I've done it, I'm going to have, N1 is equal to UX cosine theta. N2 is going to be Uy cosine theta, or sine theta, and so on, times K1, times K2, times whatever. So I'm going to write all the N in terms of these unknown U's. And then I can put them into the equilibrium equations for the free joints. And now the beautiful thing is that the number of the displacement now is always equal to the number of equilibrium equations. They are the same thing. the equilibrium is along the displacement that are free. So this is always solvable. Once you solve it, you know use, you back substitute, you got your solution. Okay, so it's a beautiful kind of approach with a lot of algebra and a lot of scalar products. So you guys you do not need to do it, but it's good that you know about it. This whole concept of the fact that the displacement is the master of the game is a very important concept. And it's used for all kinds of computational methods in solid mechanics. Because from the displacement, like we did with the bars, if I give you the displacement, you get the strain. If you have the strain, you get the stress. If you have the stress, you have the axial forces. So knowing the displacement field of something is knowing the solution. Okay? So